Hi, welcome to Ordinary Differential Equations. Today's topic is going to be about Laplace transform. Laplace transform is a method for solving differential equations. It's a kind of a detour method. We take a differential equation, apply this transform to it, and then it's going to transform it to an algebraic equation. A very simple algebraic equation. We can solve that and then do so-called inverse Laplace transform. So schematics of it's kind of like this. You have a differential equation, ordinary differential equation. We are going to apply Laplace transform to it, show it by script L. When we do Laplace transform, our differential equation turns into an algebraic equation. Algebraic equation essentially as simple as saying 2x plus 3 is equal to 5 or something like that. So that's going to be very simple to solve. So we are going to solve that algebraic equation. So we get a solution of the algebraic equation. Then we take that and then apply so-called inverse Laplace transform to it, L inverse. And we are going to get a solution of the original differential equation we had in our mind. So what we are doing is that we are going to go through this detour as opposed to going straight, which is what we have learned throughout the semester. When we take this detour, we say we are solving the equation by applying Laplace transform. Well, we keep talking about it, but what is Laplace transform? Well, in pre-calculus, you learn about functions like square roots, logarithm, exponential, sine, and cosine. These functions, they take a number in and then they give a number out. Like if you give 25 to square root function, it gives you a 5. Then you come to calculus and then you learn about operations or operators. So most important of them is differentiation. You take a function like an x cubed, you take a derivative of that, you get a 3x squared. So that is an operation that you learn. Next level up here is the concept of transforms. Transforms, like operations, they take a number in, they take a function in and produce another function of another variable out. So in differentiation, you start with, say, x cubed, you get 3x squared. In these transforms, you start with a function of, say, time, and then you get a function of some other variable. The primary among these things that we are going to study is Laplace transform, but there's a very long list of them. You can find at least 24 of these kind of transforms. The more prominent among them are Laplace and Fourier transform, named after two French mathematicians. So after all this general talk, what is a Laplace transform? Laplace transform is defined for certain type of functions. So we have a function f that is pretty much all the time a function of time. We multiply it by a special kind of function. We call that kernel. The kernel for Laplace transform is exponential of minus st. So s is our new variable. We take this combination and integrate it over the domain from 0 to infinity with respect to the variable t. What comes out of this process is going to be some function of the variable s. We have two ways of indicating what the output is going to be. One style, similar to what you had in integration, is to use the capital letter associated with this lowercase, and that's going to be f of s, is a function of s. The other style of referring to this thing is to use the script L and say we are applying it to the function f. Every now and then we use that. Most often we are going to use this one. Okay, our process is going to be several-fold. One is just to go ahead and practice with this concept to get a sense of what it is, and that one we are going to carry out by taking a set of functions that we see very often in this course, familiar functions of exponentials and polynomials and trigonometric functions and so on, and apply this thing to just get our feet wet with respect to what this thing is. Another topic next to this is, well, what's the motivation for this thing? Where does it come from? That's going to be kind of icing on the cake, as so to speak. We are going to have a brief discussion on that one as well. What is the origin of this? But the idea again is that if you have a differential equation, you are going to apply this operation to it. That is, we take that equation, multiply it by exponential of minus st, and integrate the entire equation left and right. Everything's going to get integrated. At the end of that process, we are going to end up with a very basic equation. That equation is going to be in a new variable s. As simple as saying 5s plus 3 equal to 7 or something like that. Solving that will be trivial. The output of this is going to go through inverse Laplace transform. That is, we have the result and you want to find out what the function is going to be. That's going to be the most challenging part of this whole process. There's going to be a cost somewhere, of course, and that's where we're going to pay. We are going to apply the inverse Laplace transform and go back to what solution we had. Of course, we could solve any of these problems that we are going to do. We could do it by a straightforward method that we have learned. But the method of choice for most engineers is to apply Laplace transform because it provides them with a different vantage point to the process that they are studying. So by going through this scenic route, you learn something about the system that you are attacking and solving, and that is one reason it is chosen. There are also certain differential equations that are a lot easier to solve with Laplace transform than compared with the traditional one. We are going to come to that later in the course. So our agenda is going to be the following. We are going to start with a long list of examples. So examples are going to come into two categories. We're going to essentially make several tables, just like tables you had in calculus. In calculus, your tables were functions and the derivatives, and the general rules of differentiation, such as the product rule, or quotient rule, and so on. Here also, we are going to go after some specific functions. What are specific functions? Well, like a constant function 1, such as exponential function, like say exponential of 2t or exponential of 3t, or in general exponential of any number, constant number times t. So that's going to be a simple category for us to look at. Then we are going to look at what's the answer going to be when this function is a polynomial. Polynomial meaning what? Polynomial like t squared, and so on. So we are going to have a set of these. Then we are going to look at the trig examples. Trig example will be say sine of 2t, or say cosine of 3t, and so on. So by trig here we just mean sine and cosine. Life is not going to be easy with respect to the rest of them, maybe not even defined. So what are the functions that we are looking at? This falls in the category of the polynomials P. So this is polynomials, These are exponential functions and specific trig functions. So these functions are all fall in the category of pet functions. The pet functions, as the name implies, are the easiest one, most friendly one for us to deal with. So for each of these cases, we are going to take this number, plug it here, wrestle with that integral, and see what happens. Just like what you had in calculus, for example, there you would have learned how to differentiate these things, or perhaps integrate them, and now we are doing how do you do Laplace transform to them. In calculus, you had general cases as well, such as the product rule, like you had the issue of what is the derivative of a product, or what's the derivative of a quotient, and so on. What's an example of similar thing here? Well, we are going to have another table for the general rules. Simplest of them is, what if you have a function and you have some other function and they are added to each other? How do you find the Laplace transform of that? That's going to be the simplest case. It's just going to be Laplace transform of the first one plus Laplace transform of the second one. Couldn't be easier than that. If you have a number times a function, then Laplace transform of that also going to double. These are the only two simple cases in the entire tables that we have, and they are examples of linearity. You had the exact same thing with differentiation. If you had two functions added, derivative of the sum was the sum of the derivatives. If you multiply a function by constant, its derivative multiplies by the same constant. Same thing applies for pretty much all the operations that you learn and the transforms you learn. All of them have this linearity property. Well, how about f times g? Well, we are going to hold our horses there. We don't have any simple rules for, unfortunately, for many of these cases. We have to guard against those type of mistakes. So, in calculus we had at least something. It wasn't straightforward, but now we don't have that either. Well, there's going to be a set of other rules that we are going to talk about. Most prominently, what if one of these functions, what if you have a pet function times the general function? That one turns out to be possible for us to figure out what the answer is, but still it takes some kind of an effort. So if you have like exponential of some number times t times a function, we are going to have something to say about that. If we had polynomial times a function and we are asking what's the Laplace transform of that, we can answer that as well. So, and there's going to be a few other cases. We are going to explain that as we go along. Okay. Without further ado, let's go ahead after the simplest. Of course, the very simplest would be 0. The Laplace transform of 0 is just 0. So that is not big news. If you say, well, I have 0 in my integrand, what the integral is going to be, well, it's going to be 0. So let's go after the next one. What's the Laplace transform of 1? What does that mean? It means our function is a constant function. It's just 1. We are multiplying by exponential of minus st dt. What is the what is this integral? Well, as usual, we need some basic integration rules to be able to carry this out, and one of the basic rules is that exponential of at dt, of course, is, and the derivative of that is exponential of at over a. So I have exponential of minus st over minus s. So for the sake of this integration, that's supposed to be a constant. Next challenge is, well, from 0 to infinity. What is that? let's just be a little bit loose with our notation and just use this infinity directly as opposed to the formal way of writing a limit. We want to be done quickly, and so we are going to be a little bit abusive of notation, and we are going to write minus s times infinity. So that's what we get when we put infinity here. And how about 0? 0 times s, well, there's nothing ambiguous about that. That is just 0. And denominator is minus s. Now we talk this thing out. If s is a positive number, then that minus s times infinity is minus infinity, exponential of minus infinity is 0. And this whole thing boils down to minus 1 over minus s. And when you simplify that, you just get 1 over s. So this is a case where s is a positive number. Well, s, how about s is 0? Well, f is 0, going back there, integral of 1 from 0 to infinity, that's infinity. So that is not defined. So that's going to be infinity or undefined or something. So undefined. But if s was a negative number, if s were a negative number, minus s is positive times infinity is going to be positive in infinity. This is going to be infinity, and this is some positive number. You get infinity again, so you can write undefined, or you can just write infinity in either case. So all of the problems with most problems with Laplace transform, we are restricted to a particular range of values for s. That is, the result of the integral might not make sense for every possible s, that you might limit yourself to some particular value. So in this case, for 1, we got that Laplace transform is 1 over s, and this is only good for s's that are positive. Well, once we do that, what's the Laplace transform of 2? Well, it just doubles everything that we have. It's going to double from beginning to end, and of course we are going to have 2 over s. And same fashion, if you have Laplace transform of 3, that is going to be 3 over s, and so on. So if you wish, you can, instead of 1, you can write c for a constant, and then Laplace transform over it is c over s. But that's a little bit unnecessary clutter. You can just keep it simple. Laplace transform of 1 is 1 over s, and then have a side rule here which indicates the linearity. If you multiply it by some number, you're going to multiply the Laplace transform by that number as well. So instead of taking each of these formulas, multiplying them by some number, and clutter our table with lots of redundant formulas, we try to be as economical as possible, because this table is going to get kind of lengthy, about 24 items in it. It's like you're fighting over real estate there, and you don't want to waste your space by redundant stuff. Okay, so we did 1. So that's going to be the plan of action, and just one by one we're going to go through this list and fill up this table. And then another issue is that you should learn the table both ways, from left to right or from right to left. Why is that? Just like differentiation and integration, you have to do it both ways. You have Laplace transform on one side, and almost all of these problems have an inverse Laplace transform attached to it as well, and that tends to be a little bit more involved, just like integration was more involved than differentiation. So if I ask you what is the Laplace inverse transform of 5 over s, what do you say it is? Well, where does this come from? 5 over s comes from just 5 the function f of t was constant 5, and that gave rise to 5 over s. Next up, next easy one, perhaps the last easy thing, is, well, what's a Laplace transform of exponential? So Laplace transform of, say, exponential of, let's write 2t. So what does that mean? Let me start with this one, exponential of 2t times exponential of minus st dt, integration over the t range from 0 to infinity. Well, I'd like you to pause this video for a minute and try to figure this thing out. Imagine you're back in calculus 1. You have one of those integrals and you want to figure out what this thing is. What do you think we can do? So did you listen to my advice? Stop and try to do it yourself. Okay, one of the basic ideas that we use quite often is this basic idea from pre-calculus. Exponential multiplication with same base. You add the exponent, and then you can, of course, break it up in the same fashion. So I can write exponential of 2t, exponential of minus st is exponential of 2t minus st, and then I can factor t. That would be 2 minus s. But we are going to see shortly it's a little bit better if we factor minus t. Let's see, what does that do? Exponential of minus t times s minus 2 dt. Well, this is exactly like the integral we just did, except that instead of s, instead of this s, I have s minus 2. So I can either copy that result or just apply the similar approach. I can integrate this thing, exponential of minus t times s minus 2. Remember, this is the constant here, divide by the same constant, and then I'm integrating from 0 to infinity. Same discussion as before. Infinity times s minus 2 minus exponential of, when t is 0, is easily just exponential of 0 over minus s minus 2. Similar conversation as before. If s is larger than 2, then this is positive. Exponential of negative infinity will be 0, and I'll have just minus 1 over minus s minus 2, and that's going to be 1 over s minus 2. If s is equal to 2, this is 0. Exponential of 0 is 1. Integral of that is infinity. We just get infinity. If s is less than 2, this is negative. The exponential here becomes positive infinity. This is also positive. Again, we get infinity. So the only case of interest for us is this one. So what is it that we got? We got that exponential of Laplace transform of exponential of 2t is 1 over s minus 2, provided that s is larger than 2. We have no use for the other cases. You can easily guess that if I had exponential of 3t, this would have been 1 over s minus 3, and then s had to be larger than 3, and so on. So long as I have a constant, So if a does not depend on t, this is going to be 1 over s minus a, provided that s is larger than a. Let's also practice some negative exponential, say minus 5t. That's going to be 1 over s minus 5, and s has to be larger than minus 5. So all told, we have one entry in our list here. We might as well clean this up somewhat and just write one case, exponential of at, so 1 over s minus a, provided that s is larger than a. So far we have two results, constants 1 over s and exponentials 1 over s minus the multiple. Notice that there is a commonality between these two. If a is 0, this becomes 1 over s, which is exactly that, and of course exponential of 0 is 1. So sometimes we can see our answers coexisting for some special values of parameter. Next, let's go after the case of polynomials. For the polynomials, we have to work a little bit harder. So let's see what would be the case for Laplace transform of just t. So what's that? 0 to infinity of t times exponential of minus st dt. We want to find out what that is. Of course, that's going to take us back to calculus. Find this by, what's the method? Let me ask you to pause this thing, calculate it, and come back and let me know what you find. Okay, so this is where we are going to use integration by parts from calculus. What do we do? So if you remember, integral of u dv was uv minus integral of v du. Another fact that we are going to use is the following, that if I have polynomial times a decaying exponential and I want to find the limit of it as t goes to infinity, well, I have two conflicting trends. This goes to infinity and this one goes to 0. Which one wins? Well, you remember from calculus that the limit is 0. Given these two facts, we have all the tools we need to figure out this integral. So let's write it t exponential of minus st dt. I choose for my u t. Whatever is left is going to be dt. So exponential of minus st dt. That's going to be dv. So that's my dv. So from the first one, I figure out that du is dt. And for the second one, I solve for v, antiderivative of this, exponential of minus st over minus s. So u times v, the product of these two, is going to be t exponential of minus st over minus s, minus product of v du, which is exponential of minus st over minus s. Du is just dt. Well, we need to calculate this from 0 to infinity, so that means I have to calculate this thing at 0 to infinity, and so is this case. Now at infinity, the limit of this, as we mentioned there, is 0. At 0, well, t is 0, so this term thankfully just drops out. Minus, and the minus becomes plus 1 over s, and what I have is exponential of minus st from 0 to infinity dt. This is the integral we just saw before. That was 1 over s times 1 over s. I'll get 1 over s squared. So in short, this Laplace transform of t turns out to be 1 over s squared. So let's go ahead and write down in for t, Laplace transform is 1 over s squared, and as before, the restriction is going to be s larger than 0. Well, we need t squared, t cubed, and in general all polynomials t to power of n. So let's see if we can find that quickly. So of course I can do this thing one by one. I can go do Laplace transform of t squared. I recommend that you do that, t squared, and see what happens, t cubed, and so on. Let's go for the main achievement. What if I have t to power of n? What is Laplace transform of t to power of n? Well, that would be same integral as before. It's t to power of n exponential of minus st dt. As before, we are going to take our u to be t to power of n, and exponential of minus st dt is going to be our dv. So du is going to be n t to power of n minus 1, and v, as before, is going to be exponential of minus st over minus s. When I multiply them, tn or u times v is going to be tn exponential of minus st over minus s, and then v du is going to be integral of exponential of st over minus s times this, which is n t to power of n minus 1. I forgot my dt here, so dt. Okay, we need this thing between 0 and infinity, and so is this one. With the argument same as before, at infinity, this loses the battle against the exponential, and the net value becomes 0. And at 0, well, it is just 0. So it becomes 0, and then I pull the s outside, exponential of minus st, and I have a factor of n as well. So let me pull out that one as well, t to power of n minus 1 dt. Well, what is this? That is what we would have faced if we wanted to calculate Laplace transform of t to power of minus 1. So what we found here is a reduction formula, that if you want to figure out the Laplace transform of power n, it is n over s of Laplace transform of t to power of n minus 1. How do we use that? Well, suppose I want to figure out Laplace transform of t squared. N is 2, so this is 2 over s Laplace transform of t. And Laplace transform of t, we just found out, is 1 over s squared. So this becomes 2 over s cubed. Let's do a few more. Laplace transform of t cubed. So that's going to be, by this formula, 3 over s. So this 3 comes from that. Then Laplace transform of t squared. A Laplace transform of t squared we just found. So this is 3 over s times 2 over s cubed, and we get 6 over s to power of 4. Can you guess what the next one would be if I had Laplace transform of t to power of 4? Well, it's going to be 4 over s times this. So it's going to be 24 over s to power of 5. So we see a pattern here, 1, 2, 6, 24, and so on. Do you remember what is the sequence? 1, 2, 6, 24. So this is, of course, 4 factorial. 4 factorial means 1, 2, 3, 4, multiply them all together. So that number factorial over, in each of these cases, the power of s is 1 more than the number we have over there, so it's n plus 1. This is 4 plus 1. So we have the following formula: Laplace transform of t to power of n is n factorial over s to power of n plus 1. So that's going to be one more achievement here. So let's go ahead, and for the case of polynomial, we have answered all of them. This is for t to power of n factorial over s to power of n plus 1, and that one also s is larger than 0. Okay, in similar fashion, Laplace transform of sine and cosine can be obtained by integration by parts. Is going to be a little bit lengthier, and there are several ways of doing this thing to perhaps make it a little bit more digestible. But let's go ahead and practice a few simple problems. Suppose I ask you, what's the Laplace transform of, say, 5 plus t squared plus t cubed. Let's put some numbers here also. Laplace transform of 5. That's going to be 5 times Laplace transform of 1 plus 7 times Laplace transform of t squared plus 4 times Laplace transform of t cubed. What's the principle we are using here? It's the principle of linearity. If you have several functions multiplied by some numbers and then added and subtracted, you can calculate the Laplace transform of individual functions and multiply by the same factors that you had before and add and subtract. The significant thing that's needed here is that these have to be constants. This only works if this is constant. So for example, we couldn't say Laplace transform of t squared we cannot think about it as the Laplace transform of t times t and consider one of these t's as a multiple and pull it outside, and any of those things. This just doesn't make any good sense. Only for numbers multiplying by known functions we can apply that. Okay, Laplace transform of 1 over s, 7 Laplace transform of 2, that was 2 factorial over s cubed, 4 times Laplace transform of t cubed, 3 factorial over s4. And you might as well leave the problem like this. At best you can maybe 7 times 2, 14 over s cubed, and then 4 times 4 times 6, 24 over s to power of 4. Let's notice what happens if you actually go ahead and take a common denominator. So it becomes 5s cubed plus 14s plus 24. Why did I take a common denominator? Really, there is no point to it other than saying that if you wanted to find the inverse Laplace transform of this, that is inverse Laplace transform of 5s cubed plus 14s plus 24 over s to power of 4, the smart thing to do would be to divide term by term. So you have these expressions. For each exponent, you write the factorial of 1 less than that times a certain number. So this 24, we break it as 3 factorial times some number, which turns out to be 4, and so on for the other pieces. Then we can track this thing back to where it came from. So going from left to right is rather straightforward. going from right to left, you have to do a little bit more algebra to get there. Okay, let's leave the trig functions for the next lecture, so this doesn't become too long. So the idea was you have these transforms that transform our equation to some new equations, to new variables, new domains. Sometimes you might think about it changing your perspective perhaps. So we are changing our perspective from functions that are functions of t or time to functions of s, which you might think as frequency or something. So the long-term plan for us would be to take an equation. Once we have all of our table ready, take an equation, take a Laplace transform of it. We are going to have a simpler equation, hopefully. Most often that's the case. And then solving that is going to be easy. And then inverse Laplace transform of that solution is going to bring us to the equation, the solution that we wanted. Sorry. Okay, until next time, good luck and God bless.